we solved more examples on one-dimensional heat transfer. We combined the conduction with the convection, and we also talked about heat generation, how to tackle problems which has heat generation involved. We learn about overall heat transfer coefficient, which is U, which can be written by a combination of resistances, heat transfer resistances. And we said that it's very useful to find, to relate the flux to the temperature differences at two terminals of the system. Okay, we learn about how to tackle the heat conduction problems with generation involved. And we did it for slab geometry. And we have found that you're going to have like parabolic temperature profiles in such cases. And depending on your boundary conditions, you can have a little different profiles, but all are actually parabolic. We talked about special cases like one surface is insulated, and in that case we learned about how to write down the boundary condition. We said when one of the surfaces is perfectly insulated, you can take the flux equal to 0, or the gradient of the temperature is equal to 0 at that surface. That was some of the things that we learned in the previous class. Do you have any questions so far? You can hear me, right? You can hear me while I share my screen.
Yes, we can hear you.
Okay, great. Now we're going to solve more problems on this one-dimensional heat transfer with heat generation. Since we talked about the slab geometry, now we're going to talk about other geometries. I want to go with continue the discussion with the cylindrical geometry. So my first example for today is going to be one-dimensional steady state heat transfer in cylindrical coordinates with heat generation and we're going to make the case a little more practical and more relevant to the everyday life, and we're going to consider a cylindrical wire, let's say solid wire, cylindrical solid wire, in which or through which an electrical current flows at steady state. Now, in my previous example, the slab example, the heat generation was due to anything. It might be like a chemical reaction. It could be electrical, like transformation of electrical energy to heat energy. But this time I specify what type of heat generation it is, so that I can actually use the equations that I learned from physics and apply it to these cases to write down the heat generation term more specifically, rather than just leaving it as like fancy R dot. Okay. Now assume that you know the current I in amperes or in short A, and assume that you know the electrical conductivity Ke in units of 1 over ohm meters, ohm times meters, and assume you know the cross-sectional area A in meters squared of the wire. Now let me write down some reminding notes, reminder from your physics classes. The resistance R is equal to, or you can say is proportional to the length of a wire and inversely proportional to the area of the wire, and the proportionality constant, as you might know, is the rho, which you call as resistivity. Resistivity. This is the resistance of the wire. And I'm sorry that I'm using this R in different contexts, but when you know the context, you know what it means. Basically, I'm writing down the dependence of resistance to the dimensions of a wire. And resistivity is basically the proportionality constant, which is dependent on the material, but nothing else. And you can also write this as, instead of rho, the resistivity, you can write down the conductivity, which is 1 over the resistivity. So that's equal to L over Ke. The subscript E is actually there to distinguish the Ke, the electrical conductivity, from the thermal conductivity K, which I'm not going to put any subscript for. Okay. Now, this is the reminder, and another reminder is the Ohm's law, and also the power dissipation, okay, or the thermal energy dissipation in volume V of the wire. So how much thermal energy is dissipated from a wire? You know that it's basically the, you can write it as the fancy R dot times volume, which is rate per unit volume times volume, which gives you the rate of heat generation per unit time. And this is basically nothing but the power dissipated. And you can write it as equal to, let's say power. This is from your physics notes. Is equal to I squared times R. This time this R is not the fancy R, and it's not the radius. It's basically the resistance of the wire. And if you actually plug in this thing here, you would find that it's I squared in parentheses L over KEA, right? And but what is the volume here? This volume is nothing but the length times area of of the wire, right? So imagine that you have a wire like this. And this is the cross-sectional area A. This is the L. And you know that the volume is just the multiplication of the cross-sectional area times the length, correct? And because of this, you can write down this fancy R. So for fancy R, and you get fancy R is equal to just this thing divided by this volume. Okay, so it's basically I squared L over KEA 1 over volume, but volume is length times area. And then after some simplifications, right, you get the following. I over A squared times 1 over KE. Okay, let's box it. The rate, volumetric heat generation rate in a cylindrical wire comes out to be 1 over KE I over A squared. Okay, that's one thing. So these are all reminders from our physics classes. Now I have an expression for my volumetric heat generation rate, so I can actually make use of it when I write down my shell balances and derive the flux as a function of position, and then the temperature as a function of position, and so on. Okay, and let's give more details about my system. And let's say the surface of the wire is cooled by convection. In air at a bulk temperature T air. Okay. And for those who are more comfortable with like plugging in numbers, let's also write down some typical values. Let's take the wire radius as a 5 millimeter one. Current I is equal to 20 amperes passing along the wire. The air temperature, let's take it at room temperature, somewhere around 300 Kelvin. The conductivity, electrical conductivity, is 5.8 times 10 to 7, 1 over ohm meters for copper. And natural convection in air has an associated heat transfer coefficient H. Let's call it HR, is equal to 10 watt per meter square Kelvin. This is a typical value for a natural convection. If you actually don't know anything about your system, you can take it as around like 10 or 20 watt per meter square Kelvin for air at ambient conditions. Okay, so these are my typical values. Okay, I'm gonna use. So let's find a temperature distribution in the wire. B, let's find the maximum temperature in the wire. Okay, so let's see whether the wire is going to heat up so much or not that much. So can I get some expectations from you? Any guess what temperature you think you're going to get for the maximum temperature? What do you think with these parameters? We're going to solve the question together. Let's see what we're going to get. So let's model our system. Now, let's make some assumptions, okay? Some assumptions. Let's assume that the wire is long. What does it mean when I say wire is long? It means you can ignore the end effects. Meaning that if this is your wire, right? Whatever is happening is majorly happening here, and this point, it's very symmetrical and it's also very homogeneous. This point is pretty much similar to this point, and this point is pretty much similar to this point, and so on. And you can neglect the end effects. So you can actually take it as like the system is not changing with your z dimension. Okay. So that's what it means. You can ignore the end effects, and so the axial direction can be taken pretty much homogeneous. Okay. And other assumption is steady state heat transfer in the R direction. It's only in R direction. We're going to assume there is not going to be any changes along either theta direction or the Z direction. And let me draw the schematics of my system, and let's make it. Yeah, I guess this is good. This is L. Okay. Let's take this as the capital R. Okay. And let's take a tin shell. So now here's the thing that most of the students actually gets confused. Now, going from slab geometry to cylindrical geometry, one thing you need to appreciate is your shell is not going to look like the same as in the slab geometry. So I'm not going to take a shell something like this. Okay. I'm not going to take the shell like this, because I need to take the shell in such a way that I have the most dominant heat transfer occurring. You know that there is no temperature variation along the z direction. Okay, and the temperature is only a function of R only. So T does not change with Z. Okay. So what it means is the following: when you take a when you take a shell, you need to take the shell in a cylindrical manner, like this. Let's get rid of this R for a moment. I'm gonna take my shell like this, and it's gonna be a three-dimensional shell, and I'm gonna have my shell extended like this. So it's like a You can call it like this is basically a real shell, right? So if you think about it, let me show. Now, imagine that this is your cylinder, and your cylindrical shell is basically something like this. It just has a smaller radius, okay? This is your thin cylindrical shell. I just wrapped it, see? It has a very tiny thickness of dr, delta r, and its length is still L. Its radius is like any arbitrary r smaller than the capital R. Okay, so this is the shell that I'm taking. If my cylinder is this is my shell. The folded paper or the rolled paper is my shell. That clear? So this is my shell, and it has a radius of r, any arbitrary r, and the thickness of it is delta r. So this outer radius is r plus delta r. Okay, and I'm going to make a shell balance in such a way that my flux is getting in the shell at r, and flux is coming out of the shell from qr plus delta r. Okay, it's basically not at the end only, so you have this flux getting in everywhere in this shell, right? This is q at r, q at r, q at r, and the exiting flux is q at r plus delta r, q at r plus delta r, and so on. Okay, so all the points on the surface of this shell, the flux is getting in, getting out. Now let's write down the shell balance. Balance within the thin shell gives you heat in minus heat out plus generation is equal to accumulation. And since it's steady state, there's no change with time, so the accumulation term is 0 due to steady state. And we have the generation, it's not 0. And I'm going to write it down. Let's start with the in term. The in is basically your flux, QR, times the area that the flux enters. This is very important. Please pay attention. I'm going to multiply the QR with the area that the QR penetrates into. And the area is basically, let me show it here. This is 2 pi r times L. It's basically the area of the paper that I showed you. It's basically this 2 pi r times L. Okay, that's the area of the shell that the heat flux penetrates into. So it's 2 pi r. This is lowercase r because it's the radius of my shell times L. But you calculate this at r is equal to r. Minus the out term is still qr times 2 pi r L. It's not r actually, it's r plus delta r, but I'm going to take it into account here. I'm going to evaluate it at r is equal to r plus delta r. Okay. If you have any question, ask it now, because I know it might sound a little complicated. Please let me know if you need any clarification with this. Plus, the generation term is the fancy R per unit volume times the volume itself, and the volume of the shell is the area of the shell, 2 pi r L, times the thickness of the shell, which is delta R. Okay, make sure that you understand that this is the volume volume of the tin shell. Okay. That's equal to 0. Now let's divide everything by 2 pi 2 pi L delta R delta R. I'm not dividing by R because although I cannot simplify the R's, because this R, and this R are all different R's. This is basically the R calculated at R plus delta R. So it's changing. The R is changing with R. So I cannot simplify it. It's unlike the L's. L is constant through the, when you change the R, the L does not change. So you can actually get rid of the L's, but you cannot get rid of the R's. So that's very important. So please pay attention to that part. Okay. And you get something like QR R calculated at R minus QR R calculated at R plus delta R divided by delta R plus fancy R dot times R is equal to 0. And let's take the limit as delta R goes to 0 for a very, very, very thin shell. You find that this term on the left-hand side, this entire thing, is the negative of the derivative of this QRR. Okay. And that's also one of the reasons that you cannot take the R out, because you know that the R depends on R, so you cannot take it out of the derivative because you're taking the derivative with respect to R plus fancy R dot R is equal to 0. Okay. Now I'm going to rearrange this. I'm going to say D QRR is equal to fancy R R dr. Now I can take the integral both sides. Fancy R that is constant, but the lowercase r is not constant. And so you have QR estimate QRR is equal to fancy R. The integral of r dr is r squared over 2. R squared over 2. Plus there's always some constant to be estimated using the boundary conditions. Okay. And one thing you actually can say is this equation should hold for r is equal to 0. So that means r is equal to 0 in your boundary, right? This is not a hollow cylinder, it's just a solid cylinder. So r is equal to 0 is in your domain. So you are allowed to plug in r is equal to 0. For r is equal to 0, QR must be finite. We're going to see later that it's basically 0, but it doesn't matter at this point. If you plug in, you're going to see that this argument gives you 0 is equal to C. So, so this is, yeah, C is 0. And then the QR R comes out to be fancy R squared over 2. If you do the simplification, divide by R, QR, the heat flux as a function of radius is nothing but the fancy R over 2 times R. This is the heat flux as a function of R. Any questions so far? Okay. Now, what we can do is as follows. You can actually write down you can write down a boundary condition, for example, at R is equal to capital R at the surface. Oops, let's not make it fancy R. R is equal to capital R. Let's call the temperature T is equal to Ts, T surface, right? And at that point, from Newton's law of cooling, you can write QR at capital R is equal to H times T surface minus T air, right? And then you can plug in the capital R and QR, and you find that fancy R dot over 2 capital R is equal to H Ts minus T air. Okay. And you can solve for the surface temperature. The surface temperature comes out to be T air plus T air plus fancy R dot R over 2H. Okay. Now, let's find out the temperature profile. So let's see. Let me keep writing here. Maybe I should do it here. Temperature profile. To be able to find out the temperature profile, I need to relate the flux to the temperatures. Because I have the flux as a function of position, now I want to have the temperature as a function of position. And the Fourier's law comes to the rescue. It's always what we do. We write the Fourier's law to find the relation between the temperature and the flux. Okay. It says QR is equal to negative K del T over del R in cylindrical coordinates. That's equal to, from here, let's call this equation 1. Q is equal to fancy R dot capital R. Oops, sorry. It's not capital R. Fancy R dot divided by 2 R. Now I'm going to solve for temperature. So if you write down dt is equal to minus R fancy R dot divided by 2k R dr, and you take the integral, this term is constant. You need to take the integral of r dr, and you find that t is equal to negative fancy r dot over 2k r square over 2 plus some constant, right? What you can do is basically you can write down at r is equal to capital R, the boundary condition, T is equal to TR, which you already estimated here. We know the TR from this calculation, right? I call this TS, I'm sorry, let's call this TR. Temperature at R. Yep. T is equal to TR which is basically equal to T air plus fancy R, capital R, over 2H. And then I plug it in this equation and I find out T air plus 2R over 2H is equal to minus fancy R over 2. Sorry, this is 4K. You can combine this 2 and 2 and you can make it 4. Okay, good. It's 4K. Capital R squared plus C. You can solve for C. T air plus over 2H plus squared over 4K. There you go. So that's the C. So the temperature distribution T comes out to be, if you plug in this C here, minus that over 4K. After rearranging, you get R squared minus R squared plus T air plus fancy R over 2H, I guess. Any questions so far? Okay, so that's the temperature profile. That's the answer. And now let's calculate the maximum temperature. And T max is T is equal to T max is where the derivative of the temperature with respect to R is 0 because it's a maxima point. And it's basically, if you actually write down the derivative of this thing, if you combine these two things, if you take the derivative and equate to 0, then you're going to find out that this happens at R is equal to 0. Okay. And you need to find out the temperature at R is equal to 0. So T is equal to T max is equal to T at R is equal to 0. You just plug in this R is equal to 0 in the formula, and then you find out it's positive R dot over 4K R squared plus T air plus fancy R dot R over 2H. That's the maximum temperature. Okay, and you plug in the numbers, and if you take care of the SI units, you convert the millimeters to meters and so on, you're going to find out that it's going to be a good exercise for you. T max comes out to be 300.28 Kelvin. So the wire doesn't actually heat up that much with the given numbers. Okay. Okay, before I finish, before I move on to the next module or next problem, do you have any questions? No? Okay. One question that I would like to ask is, do you know why we are curious about maximum temperatures in engineering? Why am I curious about the maximum temperature in a wire as an engineer? Any idea?